Welcome back to the video lecture series for Introduction to the Art of Programming using Scala. In the last video we started talking about grids and how we can use grids as a spatial data structure. So if we have a bunch of points and we're trying to find neighbors for a point, we can lay things out on a grid and then we can do our searching on the grid. And we started writing the code to actually do this. We made our grid neighbor finder so it extends the neighbor finder. We decided we're only going to work in 2 dimensions here to keep things simple. And we had gotten to the point where we were writing our make grid method. To keep things simple again, we're assuming that the region that we're working on is close to square, and so then the number of cells on each dimension, both x and y, needs to go as the square root of the number of points if we want to have roughly 1 point per cell. And the grid that we are going to make here is a 2-dimensional array of lists. So this has been set up. The next thing that we need to do is we need to find the minimum and maximum values for the x and y in both of across our points. So I'd create variables for the minimum x. I'll type these in long way first, and we'll see if we could simplify this some. So we could take points dot map to, I'm going to use the rocket notation here, sub 0 gives us the x, and then dot min. Because I'm going to wind up duplicating this same points dot map thing for the maximum, I think I will create a variable called x's, and that way I can make the minimum x to be x's dot min and the maximum x be x's dot max. Similarly, the y's, pulling out index 1, and we get our min and max values there. Now we need to run through all of the points and append them to the appropriate lists in our grid G. So I'll run through every point in PNTS. The bin value in x is equal to p sub 0 minus the minimum value of x, that quantity times the count divided by max x minus min x. And just to be on the safe side, because it turns out that when you're actually equal to max x, you'll get count instead of count minus 1. So I am going to take the min of that and count minus 1 so that it can't go over the top bounds. And then I want the same thing for the y dimension. Okay. Note that this is just a linear scaling here. When the point value is equal to the minimum, this is 0, and 0 we multiply and divide and we still keep the 0 value, and 0 should be less than that. However, if this is equal to the maximum, then it turns out that this term is equal to this term, so we have something divided by itself, which is 1. We multiply by the count, and we get exactly count. We need to pull that down to count minus 1 here, and so that this stays in a happy range. And then I want to say g sub x bin sub y bin cons equal that particular point p. I need to cast this to an int. Okay. And I did that before the min. That was intentional there. And so this will, after calculating the bin value where we are located spatially, so if we go to our picture, the x bin is which one of these columns we're in, the y bin is which one of these rows we're in, and so the combination of those two tells us where we are, and so we're just going to cons that onto the list that happens to be at that bin location. That finishes off our make grid. Now we need to decide how we're going to visit all of our the other values. The simplest solution for this, if I assume that search distance has to be smaller than the grid size, would just be to run through the adjacent cells. And so I'm going to start off writing that. So the first thing that I have to do is, like I did down here, I need to calculate the bin value. And this is not, I called this P and T here. And you'll notice that in order to calculate this, I need these min and max values, in which case it's helpful to elevate those out so that we're going to store them and we can use them. Notice that my count also needs to be something that I'm stored because I need to be able to use it for every single time I call visit. So this calculates where this is located, and then I want to have a for loop that's going to have two iterators. And actually, you know what, the way that I prefer to do this, oh, let's do this way. For x in x bin minus 1 to x bin plus 1, if x is greater than 0 and x is, and let's do greater than or equal to 0, as well as x is less than count, y in y bin minus 1 to y bin plus 1. Same type of thing here. If y is greater than or equal to 0 and y is less than count, then we need to do something. So to make this code clear, let's look at our picture. Again, I want to find the nearest neighbor, say, of this point right here. So first I calculate what bin it's in, the x bin and y bin, and then I need to run through the loop of the things around that. So this is x bin minus 1, this is x bin plus 1, and then I do the same thing in y. What if I was searching for this particle though? Well, then some of these things around it aren't valid bins, and that's why I need to have these ifs to make sure that we are on a valid location. Okay. So, at this point I have an x and y bin that I want to do my comparison to for this point, and I just need to run through all the particles that are in there, and if the distance is small enough, we'll do our calculation. So let's do 4. I already have my for loop here. We're just going to extend it out for another level. So P2 in the grid located at x, y. You'll note here this is why I have to do these checks against count. If the dist, and let's go back to our neighbor finder, dist from P1 to P2, so of the point that we're searching for to P2 is less than or equal to search dist. I don't even think I need some curly braces here. Visit P2. Okay, and there we go. Now once again, this makes the assumption that we're always doing a search radius that is no bigger than the size of this cell. That's not necessarily always a safe assumption. In practice, if I were writing this code for example, simulation, I would actually have slightly more logic to calculate the size of the cell, so it isn't just based upon the count. It would be based upon what search radius I was likely to use, so that was a safe assumption. If we weren't going to guarantee that's a safe assumption, then the other thing we need to store in here is how big this grid cell is, so that then instead of saying -1 and +1, we could say search distance divided by the size of the cell, and we'd take the ceiling of that. But for this video, we're not going to make that assumption. We're going to assume that our search radius is small and leave the code as this is for now. We should come back and test this as well as our brute force search